So good afternoon, everyone. Welcome to this edition of the NITheCS Colloquium on our regular Monday afternoon time. This afternoon, I'm very happy to have as a speaker Professor Michael Laidlaw. And I'm very happy about the title of his talk, because for the first time we have a kind of a historical talk, which is, there's always a first time. So thank you very much, Michael, for offering that to us this morning. And I'm also very, very happy to have with us Professor Ahmed Bauer, who was many, many years ago, and he might mention it just now, a colleague of Michael at the University of Durban-Westville first, and then the University of Natal later. So they know each other since many, many, many moons. Yeah. And with us is as well Ilya, that most of you know, because he's our standard co-host. Yeah. So, Ahmed, may I kindly ask you to introduce the speaker? Thank you very much for being with us this afternoon. Yeah.
Thank you so much, Francesco, and thank you for inviting me to do this. And it really is a wonderful pleasure, really, to introduce Michael. The first time I met Michael was in 1984, sorry, 1984-85, at what was then the University of Durban-Westville. And actually, the main point of kind of intersection was in the basement of the H block, like, because that's where the computer labs were. And I used to like go down there. I was at that time I was kind of had just been employed by Krish Bharatram in the physics department as a junior lecturer, and I had just started a master's program on nuclear spectroscopy, and I was absolutely in need of help and so on all the time. So I would kind of saunter down there, and because I had to do a whole lot of computer modeling and sort of this new detector that Krish Bharatram and others, a three-dimensional detector that Krish Bharatram and Rob McMurray had kind of put together, and Roy McMurray, sorry, had put together. And so I went down there quite often, and I used to intersect with Michael there mainly. So I just want to also say that, you know, I discovered at that point in time that actually Michael had done a PhD in theoretical physics. Right? I didn't know at the time that it was that his supervisor was Cecile DeWitt, right? The longtime partner of Bryce DeWitt, right? And that his work, I mean, I discovered at that time that his work was mainly in this area around topology and physics, and this intersection between kind of topology and in particular the work on kind of path integrals and so on. So I was fascinated by that, of course. And at that time, of course, in South Africa, there was, except for the University of Cape Town, there was very little going on in the area of particle physics. And when I then finished with the MSc and got a scholarship to go to the UK, the first thing I did was look for a place where I could do particle physics, partly because I had been intrigued by this kind of this interactions that I had with Michael. Michael was head of Department of Computer Science and at University of Durban-Westville. And then after that, I moved to University of Natal, and then sort of had the opportunity of having Michael come to University of Natal, and then we intersected again at the University of Natal. And I mean, I'm not going to say much more, because I think that I'm really anxious and keen to hear about just those early years of the intersections between topology and physics, right? And because he was in it at the very beginning, almost. You know, I think Cecile DeWitt moved to the University of North Carolina in the early 1950s, I think, and it was very much at the time when there was just a growing intersection, if you like, between topology and theoretical physics. So with that, Francesco, I'm going to, should I just hand over? Should I hand over back to you?
Yeah. That's Ahmed. Thank you very much for the very nice, also historic introduction. Yeah, and Michael, now it's my pleasure to ask you to start your presentation. And if you want to share your screen, now it's the time to do that. And while you do that, a quick reminder to the participants to please make use of the Q&A facility at the bottom of the screen to ask questions. And Ilya will monitor them during the talk. So Michael, we are all very keen to listen to your talk. Thank you very much for offering it.
Well, thank you, Francesco. It's a real pleasure to me to be on your webinar. And really must say, and a special thank you to you, Ahmed, for taking the time out from your hectic life to introduce me to the audience here. I did, when I was speaking to you privately before everybody joined in, that I regarded my life as being on the bicycle, whereas I thought that you were actually on the Harley Davidson, and you soon overtook me in your path to your present high state in South African academics. I'm really happy that you found the time to introduce me. Thank you, Ahmed. I'm now going to share my screen. So I don't know what happens now exactly, but I'll press this green button.
Yeah.
And somehow. Yes.
Perfect.
Colloquia are often where new ideas are first presented. This one will be very different. It will be about my work in quantum mechanics and topology 50 years ago. I hope you will find this history lesson interesting and enjoyable. Certainly, I had a lot of fun. I really did have a lot of fun assembling these recollections. Now, in the past, I used to deliver my lectures off the cuff with sometimes alarming results, but anyway, that's what I did. Now, with this novel and remote means of presentation, I'm reluctant to extemporize. So I'll be reading to you what I have prepared. Those familiar with the discovery of anyon quasi-particles and excited by the potential they have for quantum computing will appreciate that there is a current relevance. At the time, my work was regarded as esoteric and with no practical applications. So I have been astonished to learn of its resurrection. I took my undergraduate degree at St Andrews University in Scotland, and from there I went to the University of North Carolina at Chapel Hill in 1967. Cecile DeWitt was my research supervisor. Now, she was a really remarkable person. She was born in France, and as a young woman embarked on a career in physics. Sadly, the devastations of World War II resulted in personal tragedy and the interruptions of her studies. She briefly went to neutral Ireland. Ireland was neutral. At least the Republic was neutral in the Second World War. And there she worked with Erwin Schrödinger, who'd also obviously moved to Ireland. And then in 1948, she was, much to her surprise, I might add, invited to the Institute for Academic Study in Princeton, the Advanced Study in Princeton by Robert Oppenheimer. Assembled there at that time were many eminent physicists and mathematicians, Einstein, von Neumann, and Gödel, to name a few. It was there that she met and married her long life partner, Bryce DeWitt. She was renowned for her work in mathematical physics and ended her days as emeritus professor at the University of Texas at Austin. However, she is best remembered as a great enabler for other theoretical physicists. In 1951, she established a summer school of physics at Les Orges in the French Alps. Over the years, an astonishing total of 52 Nobel Prize winners attended that school, either as lecturers or students. For her achievements, she was awarded the French Legion of Honor in 2007. And in 2019, the French Academy of Sciences created a prestigious physics prize in her honor and memory. Cecile and Freeman Dyson met at the Institute of Advanced Studies and remained friends throughout their life. Both of them shared the belief that stability, complexity, and diversity are the three most profound characteristics of nature. Furthermore, these are scalable from the extremely large cosmic dimensions through our everyday experience and down to the atomic and subatomic levels. There are only 90-odd natural occurring elements. That is all that nature needs to build the most extraordinary, complex, and diverse things. Most elements are unbelievably stable, and their atoms can exist for billions of years. In the early days of the last century, physics began to investigate the structure of atoms and the nature of their stability. To do this, some violence was required using electricity. Classical physics, sorry, let me start that sentence again. To do this, some violence was needed to induce instability using heat, light, and electricity. Classical physics was unable to provide an explanation for the experimental results. By 1930, the new ideas of quantum mechanics had become firmly established. And that theory, together with Pauli's exclusion principle, beautifully explained the features of atoms and their structure and why atoms are so incredibly stable. It took longer to move away from things that were static towards an understanding of the dynamics of particle interaction at the quantum level, difficulties of action at a distance, time delay, radiation inertia, self-interaction, and relativistic invariance were serious challenges. Richard Feynman was awarded the Nobel Prize for his theory of quantum electrodynamics. I confess I never properly studied his work, and I have no idea how things may have changed in subsequent years. Cecile met Feynman while she was at the Institute of Advanced Studies and was influenced greatly by his path integration formula of quantum mechanics. She in turn influenced me and steered me in that direction, indicating that the ideas from differential geometry could be fruitful. At that time, path integration was not well regarded. Even Feynman called the formulation a beautiful woman now becoming old, whereby greatly offending Cecile. Insultingly, it was also called psychotherapy for those unequal to the stresses of real physics. And like any good insult, it had a kernel of truth. Mathematically, it was on rocky ground. It did not lend itself to at all to calculations, except perhaps to numerical calculations on the computer. I liked it because it gives you a bird's eye view of quantum processes. Differential equations are inherently myopic. It is a tool for thinking about quantum mechanics rather than for actually doing it. And this I will now present with a wide paintbrush. The coin being tossed here is a 1960 South African penny of Queen Elizabeth II. There you go, 1960, Queen Elizabeth II, South Africa, Zuid-Afrika. I have been unable to resist the temptation of throwing in a bit of pneumatics into this talk. A marvelous occupation for the elderly. I was 16 years old at the time this coin was made and already learning about the Bohr hydrogen atom. That is not to say, relative to all the other things that excite a boy of that age, that the hydrogen atom was particularly high on my list. If the outcome is heads, you can infer that the trajectory must have been along the red paths. Any trajectory along the green paths will result in tails. You could check your inference with a high-speed camera. Indeed, with sufficient information about the starting conditions of the trajectory, you could in principle project the outcome. One of the tenets of the scientific method is repeatability. That is to say, if you do the same experiment over and over again, you should get the same results each time. That baby goes out with the bathwater at the quantum level. Take your pick of what this coin toss of a quantum penny symbolizes. You can infer which of the two possible paths leads to the separate result. However, there is now no way to confirm your inference because to do so will be to disrupt the trajectory. You have a dilemma. Either the path taken was the red one or the green one, but you can't tell which. The problem here is one of semantics. If it's impossible to distinguish between two things, the language you use should not permit the idea of a distinction to arise. This is the great reset of quantum mechanics. Get rid of the word or and replace it with and. The dilemma then disappears because it's unthinkable. The hard work now remains because you have to devise the mathematical framework to accord with quantum observations. More about that later. Now is the place to bring in Schrodinger's poor old cat, long dead, whether by radioactive decay or not. By dispensing with the word or, we are left to face with the bewildering idea that before we actually look at the quantum penny, it has to be in both the red state and the green state at the same time. The act of observation has to be the thing that miraculously and suddenly causes resolution. People were battling with the philosophical problem in the 1960s, and for all I know, they still are. Bryce DeWitt gave a series of lectures at UNC on the Everett Wheeler many universes interpretation. Indeed, he did much to popularize the idea. I had enormous admiration for the man. And unfortunately, in return, I was treated like a semi-idiot because I probably didn't understand his lectures properly. I do recall one conversation we had in which he said, "I only believe something exists if I can kick it." I am reasonably sure now that Bryce did not really believe in many universes. Either he was fulfilling the obligations of some research grant, or he regarded it as those of us with a lower IQ would treat a crossword puzzle. There was so much in physics I didn't understand that it didn't really concern me that much. But here was one issue where I was happy to enjoy the company of many great men. The previous diagram suggested that there was just one path between the initial state and either of the two final states. That is an assumption which asserts that we know the trajectory of each of these paths. That is untenable because we are not permitted to know anything about what happens between the initial and final states. That leads to a horrible situation where we must consider all the myriad of possible paths, each of which has to be followed concurrently. You have to admire not only the intelligence, but the tenacity and courage of early physicists like Feynman, who followed onwards from there. Schrodinger's equation is based on the Hamiltonian of classical mechanics. In the Hamiltonian formulation, the way to get the trajectory is to specify the initial position, the momentum, the start time, and iterate forwards from there. An alternative classical formulation is the principle of least action. In that method, the initial and final positions are the given conditions, and the classical path is the one for which the path action is the least between the start and end times. The Hamiltonian method is easier to handle mathematically. From experience, I can tell you for sure that the least action is far better suited to numerical computations. This is a familiar diagram straight out of Mechanics 101. For each possible path, there is an action functional of that path. So here is the Lagrangian, dependent on time, located at this point in the path, the start point A, the finishing point B, and the action, which is a functional of the path, is integrated from the start to the time of the Lagrangian over the path. The jump to quantum mechanics is to associate with each of the myriad of possible paths a complex number, giving the probability amplitude for a transition along that path. So there's the probability amplitude. Notice that it depends on the action functional. This is the probability amplitude for a transition from A to B along that specific path Q. To obtain the probability amplitude of a transition from A to B, you add or integrate over all the individual amplitudes. So this is this gruesome thing here, the integral over all the possible paths between A and B. And that gives you the complete probability amplitude of the transition. As I said, it's pretty gruesome, It is an integration of a complex function of a functional, not a function. I'm not sure if the mathematicians are now happy with this idea. Fortunately, you have a lot more leeway in mathematical physics, and it is not too hard to show that this formulation is, and that of Schrödinger's, is equivalent. Things are not too bad because you can fragment the path, boing, 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 and so on, into small time segments. When you do that, the contributions from the non-classical paths cancel each other out, and the calculations become possible. As in classical mechanics, devising numerical methods for quantum transitions is fruitful. I am told that identical twins often bamboozle their parents by swapping identities. I am not sure what scale it becomes absolutely impossible to distinguish between two identical things. Certainly, fundamental particles have no individual identity at all. There was an odd idea in the 1960s, I think maybe due to Feynman, I'm not sure, that there was only one electron in the whole universe. And to misquote what was said about the Scarlet Pimpernel, you find him here, you find him there, you find him everywhere. Now consider two indistinguishable particles, one of them here in Hilton and the other up there in Pretoria. Well, the alternative is that B is in Hilton and A is in Pretoria. Either one is possible, but you can't tell which is which. Again, the dilemma is one of semantics, and the resolution is to replace or by and. In terms of the wave function of the two indistinguishable particles, we must have a superposition of the wave function for each of the two possibilities. A familiar and somewhat hand-waving argument leads to the alternative and distinct types of superposition, one for fermions and the other for bosons. As a consequence of that, fermions obey the Pauli exclusion principle. The exclusion principle is important because of it dictates the stability of atoms. Because of this, Cecile encouraged me to look at how path integration could give insight into the behavior of systems of indistinguishable particles. The diagram shows the configuration space of two such particles in one dimension. The two dots represent the indistinguishable states. Tracing out the evolution of this configuration space is a mess because there are two mirror image trajectories, and for each time increment, there is also a crossover path where the particles interchange identities. So you can have this path evolving like this, and then a mirror image going like that, and then all the way along the paths which correspond to the interchange between the two particles. Think of the configuration space as a piece of paper. If you fold it over along the dotted diagonal, the two indistinguishable states become one point, and now you're in business. The nice thing about a talk like this is that you can start off with a simple inception of an idea. Now, the act of folding the paper is mathematically a topological change. For a system of n indistinguishable particles in 3 dimensions, the equivalent topological change is found by taking the configuration space modulo the permutation group. With the proviso that no two particles can simultaneously occupy the same position, that space is multiply connected. Being inclined to form mental models, physicists can readily relate to geometry and topology. In contrast, differential calculus can become rather ethereal. The simplest example of a multiply connected space is the circle, or a simple rotator. Paths from A to B can go clockwise by the red path, or anti-clockwise by the green path. Clockwise by the red path, oops, or anti-clockwise by the green path. Now imagine that the circle is a cross-section of a cylinder and that there is a red rubber band thumbtacked on the surface at points A and B. You can distort the rubber band as you wish, but by no distortion can you morph it into the green path, except of course by lifting over the top, and that's cheating. You can imagine looping round the cylinder n times. All distortions of the path will be characterized by n circuits. To simplify things, consider now the closed path that starts and ends at the same point A. There will be the null path, which can be morphed into a path which is just stationary at the point A. Then there will be the paths which go around clockwise, 1, 2, 3, and so on times. Conversely, there will be the paths that go around anti-clockwise, 1, 2, 3, and so forth times. Two paths are said to be equivalent if they can be morphed by continuous distortions into one another. The set of all equivalence paths is called a homeotopy group. You can join two paths in a head-to-tail fashion. That combination can be regarded as an operation between paths in different homotopy classes, giving a path in a third class. It is reasonably obvious that in this case, the collection of homotopy classes together with the join operation is going to form a group isomorphic to the group of integers under addition. So many wonderful and formative ideas in all areas of human endeavor flourished during La Belle Époque at the turn of the last century. It was during this time that mathematicians were combining the ideas of geometry with algebra. Out of this came the understanding that every multiply connected topological space could be characterized by an underlying fundamental group. The topic of my PhD thesis was on how to do path integrations in multiply connected spaces. Unfortunately for me, the physics department typist who was transcribing my handwriting was the girlfriend of the mathematics professor who had taught me about topology. So he had prior warning of what I was doing and launched a salvo of criticism at Cecile for the way in which I was abusing his subject. My opinion was, in fact, that I just put his nose out of joint by doing something novel before he thought about it himself. Cecile must have won this interdepartmental contest, for the degree was awarded by the panel with congratulations for all the physicists present, albeit with one dissenting mathematician. for each homotopy class, there will be a probability amplitude for the transition A to B obtained by path integration over all the paths in that class. So you here have got all the paths in this green homotopy class and a partial probability amplitude K alpha for all the paths in H alpha, and similarly with K beta and K gamma. Now, because the paths in different homotopy classes cannot be deformed into one another, if they could be deformed into one another, of course, they would be in the same homotopy class. Because the class can't be deformed into one another, it would be incorrect to assume that the individual contributions are in phase with one another. So you don't just add them together. They're ambiguous in the sum to the extent of a weight factor. And the starting point is to assume that the contributions are weighted by arbitrary complex numbers. That's these numbers here. And the sum is over all the homotopy classes of all the partial probability amplitudes associated with that particular homotopy class. I will spare you the mathematical arguments that lead to the determination of these weight factors. More to the point, I will spare myself the anguish to try and remember were I even able what the arguments were. For those interested, they can be found in my physical review publication or in my thesis, a copy of which can be sent to you by email. The results are reasonably obvious anyway. The weight factors must form a scalar representation of the fundamental group. There will be as many distinct means of propagation as there are scalar representations. This is a superselection rule because transitions between different means of propagation are prohibited. In particular, for systems of indistinguishable particles, the fundamental group for the modified configuration space discussed previously is the permutation group. There are two scalar representations for this group. The first gives Bose statistics, and the second gives Fermi statistics. So it's +1 for all the permutations, plus or minus 1 for even or odd permutations, and Bose is this one, and Fermi is that one. My path through life, I have little claim to be a physicist. In 1971, I could see no way forward from my 2 years of research. There was no apparent application for my work in particle physics. The only possibility seemed to me in the construction of topologies created in the laboratory. Among the experimental physicists at UNC, there was no enthusiasm for supercooled thin films, in thin films peppered with little holes, or even in thin films coated on tiny donut shapes like a torus. In the end, the decision to leave physics was made for me by Uncle Sam, who ordered me to report for basic training with a view to sending me to fight in Vietnam. I changed horses and eventually became a computer scientist in South Africa. My department was on the campus of what is now UKZN. I was located in the engineering building with a view across to the science building where Francesco is probably now sitting. I only recently became aware of the revived interest in my work as a physicist when I was contacted by Philip Stamp, a physics professor at the University of British Columbia. The outcome was 2 lengthy Zoom meetings between the 2 of us and Harvey Brown at Oxford University. Their intentions is to string together a history of the development that leads to the discovery of anyons and their application to quantum computing. When completed, they hope to publish this account in Physics Today. I find the linkage between my early research and my career enormously pleasing. The elderly, as their productive abilities decline, are inclined to ponder. I can be forgiven, therefore, if I speculate that this linkage between the disciplines of physics and computer science could be more than superficial. Computer science is like upside down physics. Physics takes complex things and breaks them apart in an attempt to discover the basic building blocks and the interactions between them. Computer scientists are given the basic concrete building blocks and the defined rules of combination, and from there construct complex things, some of which can simulate real life. However, the language that each of them uses imposes a different discipline on their thinking. One language is discrete and digital, and its expression is suited for the computer. The other works with continuous, and the analog nature of differential calculus is suited to the human brain. This contrast is akin to the 2 cultures of C.P. Snow, art and science. His lament was that the division imposes limitations on the possibilities of our thinking. My hope, not without some grounding on experience, is that quantum computing will become the liberating bridge that frees physicists and computer scientists from these constraints. Thank you, that's everybody. Thank you, everybody. That's the finish of my presentation to you.
Yeah, Michael, thank you so much. Thank you very much for a very nice talk that brought us back 50 years and showed us again that sometimes it takes a while until the proper recognition for one's work arrives. No, thank you very much. It was really very interesting also to see the environment in which you were lucky to study and to complete your PhD. That was really very interesting. Ilya, do we have some questions from Michael from our audience?
For now, I don't see any questions. But you know, maybe I can ask a first question because
please, and we can also, sorry, before you ask the question, we can maybe offer the participants to raise their hand so that we can allow them to pose their questions on their own. Yeah, please, Ilya, but go ahead.
Mm-hmm. Okay, and there is an arm. So let me first ask my question, because you know, I mean, like it's a little bit like a strange story when what you are telling us about that, like, I mean, the topological ideas in quantum mechanics was so late to be recognized. But you know, if you just kind of watch a little bit in the slightly different direction, like in statistical physics, the ideas of the topology and the topological states of matter are prominent for much longer time. And you know, the same idea of the path integrals, but so-called imaginary time path integrals, where you need to calculate the statistical sums or z-factors, those kind of topological ideas were kind of much more in favor, and physicists were much more fond of it. Have it came about any connection of your work to the statistical physics?
Well, I wish I could answer your question, but before I can answer it, I have to understand it. And that's, that you'll have to forgive me. You must treat me as a simple first-year student these days, I'm afraid.
Okay, no, because like, you know, I agree that in quantum mechanics, it's really, you know, maybe it's only happening now and really with the quantum computers or quantum computing and anyons. But in statistical physics, I think it was much more well-accepted idea and kind of well-accepted domain of mathematics, at least to the best of my understanding. But maybe we can give a chance to ask the questions to the other people who are in the call. Arun Kumar, you're welcome to ask your question.
Hello. This is not really a question, but just a comment. You know, I was a lecturer in the Department of Mathematics and Applied Mathematics at the University of Durban, Westville from 1979 until 1989. And while I was there, of course, Mike Laidlaw was in computer science. And, you know, we used to meet from time to time, especially with Ramesh Ori, who was another lecturer in the maths department. And, you know, we used to have some interesting discussions because I was just beginning to get into relativity at that time. But I never realized that Mike had actually done his PhD under Cecile DeWitt because, you know, many of these mathematicians like Cecile DeWitt, Yvonne Choquet-Brouhart, and of course, most notably, Roger Penrose, you know, had applied some very interesting mathematics in relativity. I just knew Mike Laidlaw mainly as a lecturer in computer science, but I can also add that, you know, he was one of those first people who was actually trying to use computer science to actually do various calculations in mathematics. You know, for example, things like doing differentiation and integration and so forth. And that was way before, you know, people came up with Mathematica and so forth. So Mike, it's nice to hear you again. And I must add that you gave a wonderful talk. Thank you very much.
Well, it's lovely to, I can hear you, but I can't see you, but it's lovely to hear your voice again.
Okay. I don't know. Okay, maybe we can ask Martin to ask his question. Please.
Okay. I really enjoyed your talk, and I remember reading your paper from the 1970s with Cecile DeWitt when I was a graduate student in the late 1980s. I just wanted to make one sort of interesting comment. So a lot of the mathematics of this sort of propagation, when you break it into homotopy groups, we sort of think about it as being quantum mechanical, and it certainly is. But in the early 1900s, there was this paper that I found by Karslaw, where he was trying to calculate the diffraction off of sort of an absorbing half screen, sort of in the spirit of Sommerfeld's exact solution, you know, for sort of conducting half sheet. And what he did was he, with some very clever deformation of contours in the complex plane, found this propagator where you sort of made this sort of infinite staircase around the origin. And it gives exactly the the same propagator that you had for, if I remember correctly, you know, for going around and you sort of count the winding number is you sort of doing a Harnaff bone diffraction. So it's sort of an interesting connection, the sort of model of a perfect absorber or black body screen, which in reality is a lot more complex. So thank you for your beautiful talk.
Thank you very much.
Thank you, Martin.
Okay. Darmanan, you can ask your question. Sorry if I butcher your name.
Thank you very much. Thank you, Mike, for the lovely talk. You'll remember me, Dams Babula. Of course, we were quite close at UDW. I mean, we occupied different floors, but maths and computer science were, of course, very close together. Yeah, I was interested in that part of your talk where you spoke about the mathematics involved, and in particular interested in the homotopy theory that you mentioned when you spoke about the fundamental group of the circle being infinite cyclic. Yeah, I was wondering whether you know about how homotopy theory has entered into physics. You have mentioned that you had done this work some years ago, but how has that sort of progressed in physics? I should add that I don't know any physics at all. I only know the mathematics or some parts of the mathematics, but I'd be very interested to know how homotopy theory has influenced the tackling of problems in physics. So yeah, that's my question.
Well, it's lovely to hear you, Dams, again. How's Sathya? I mean, it was a long time since I've spoken to him as well. How's he doing?
Yeah, he's well. He's well. Yeah, he is.
I pass on my good wishes to him because he was obviously a colleague of mine in the computer science department.
Yes.
And he took over from me basically and ran the department. Anyway, to answer your question, Dams, so far as I know, there was one other person that had thought about topology before I did in its application to physics, and that was Lawrence Schulman. He did a bit of hand waving, and Cecile said, well, you know, let's see if you can nail this hand waving down and make it a bit more presentable. You know, that's the only knowledge I have prior to my own work about topology appearing in physics. You know, but there could be many other disciplines, and solid state physics strikes me as a wonderful example where topology could end up. I don't know. So far as what's gone on since, I have no idea at all. Just as ignorant as you are being a mathematician, I was a computer scientist, and you know, there's yet to be a topologically shaped computer, so I've got no interest whatsoever as far as I'm a computer scientist in topology. But I understand that it is actually now significant because of these Inion quasi-particles. They apparently exist in sort of a two-dimensional plane, and as they wrap around each other, they entangle, they get tangled up rather than becoming entangled, to misquote a physics thing. And that gives rise to some kind of a topological state that you can be in. But, you know, I'm just mumbling here because I don't really know anything about it. But it does seem to me that somewhere along the line, there should be greater understanding reach between both computer scientists and physicists about this, you know, the possibility and the practical applications of quantum computing. It's something that I think scientists, computer scientists, are going to have to address when the business of creating algorithms and solving problems comes out of the quantum computer. In fact, I'm sure they're already doing it, but I wouldn't know. And likewise, physicists need to learn about the behavior of the discrete, and rather than the continuous. Physicists are really hampered. I'm sorry, Dams, you're a mathematician and you take these things for granted, but I don't think that physicists should take the world as being continuous as being for granted. It's not continuous, for goodness sakes. I mean, this little pesky epsilon that keeps disappearing to zero, and then everything falls out, is just unrealistic. That's my view. Having tried to solve differential equations in the computer, I thought, well, goodness me, the problem is not with the computer, it's with a differential equation.
Ilya, do we have more questions?
Yes. Paran, you're welcome to ask your question.
Hi, Mike. I don't have any questions, but I just want to say how happy I am to be here present and seeing you after all these years. You may or may not remember me, but you taught me in first year computer science in 1982, I think. And so yeah, I have some very happy memories of those days, and I recall that you had one of the first Apple Macs in those days, so it was a big novelty for us at the time. Yeah, so I'm very happy to meet you again, and hope you're very well and so on. And yeah, so I'm very, very happy to see you again.
Well, I'm extremely flattered that you remember who I am. I confess that I don't really remember who you are. It's okay. Bring back the memory of the Apple Mac, because that was a real change in my thinking about what computers could do. You know, this nice, lovely graphic display that you could manipulate and play with. Oh, that was a lovely machine. I can't afford one anymore, unfortunately, but anyway, that's the way that world returns.
Yeah, then Michael, it doesn't seem that there are more questions, and I'm very pleased that you had the opportunity also to interact with some of your former colleagues at University of Durban-Westfield and University of Natal, and some of your former students that seem to have fond memories of the time you taught them. Yeah. So it is now my, you know, unfortunately, all good things come to a natural end. So it's my duty now to thank you very much for your time and for the big effort of preparing a very interesting presentation that everybody seems to have enjoyed. And I hope that we will stay in touch. And you know, in the good old times before COVID, we used to invite our speakers for dinner. But at the moment, it's not possible, but we won't forget. And as soon as we are all vaccinated and that will be possible, we will make a plan. Yeah. So Michael, thank you very much. again for your really nice talk and for being with us this afternoon. Ilya, thank you for moderating the questions, and a big thank you to Ahmed Bawa for the introduction, but unfortunately had to leave a few minutes ago. And thank you very much to all the participants for being with us and for their contributions to the questions and comments and remark session at the end. So thank you very much, Michael. Again, it was really very nice. We will stay in touch. Yeah. So all the best, and everybody have a good evening. Yeah. Thank you very much.
Bye.
Thank you. Bye bye.